Good evening. My thesis project has focused on second-generation biofuel production, which involves taking agricultural waste like beet pulp or citrus peel and converting it into more valuable products like ethanol-based fuels. The reason we can do this is because agricultural waste is made up of lignocellulose, which has three key components: lignin, a sticky structural component found in most plant matter, cellulose, and hemicellulose. Now, these are polysaccharides, long chains of small sugars linked together repeatedly. To turn these into fuel, we use special enzymes called cellulases. Cellulases work because they have a cellulose binding domain, which binds the cellulose, and a catalytic domain, which chews through the cellulose in what we call a saccharification reaction. Now, when this reaction is complete and all the cellulose is gone, the small sugars produced can be fed to yeast to turn into ethanol, much in the same way we make wine. And the released cellulases can be reused by putting them in a new vat with fresh substrate from agricultural waste. But here's the problem. The cellulose binding domain is promiscuous, which means it not only binds to cellulose, but it also loves to bind lignin. But the catalytic domain can't chew through the lignin to release itself. As a result, any cellulase that binds lignin becomes stuck and cannot be reused. This means that for saccharification to continue, we have to replenish the cellulases we've lost. And as you can imagine, this is expensive, and part of the reason for why this technology is not cost effective compared to using petroleum-based fuels like oil. My job is to rescue these lignin-trapped cellulases so that they can be released, reused, and recycled. Currently, people are using corrosive sodium hydroxide and expensive detergents to try to wash the cellulases off the lignin. But this often destroys the cellulases and does nothing to actually drop the cost of production. What we propose is better, because all we're going to do is change the temperature of the reaction vessel. You see, the golden rule in biology is that structure gives you function. That means that for an enzyme to work, it requires a three-dimensional structure. But if that structure is lost, so is the function. So let's say we have a cellulose binding domain that's stuck to lignin. Much in the same way, you can heat a three-dimensional ice cube until it loses its three-dimensional structure and it melts into liquid water. You can also heat the cellulose binding domain until it melts and it loses its three-dimensional structure and its ability to bind lignin, without affecting the structure of the catalytic domain. As a result, any cellulase that's stuck to lignin gets released and can be put into a new vat with fresh substrate. And to get this to work again, all we have to do is lower the temperature. Because much like you can refreeze liquid water and regain the three-dimensional structure of an ice cube, we can also cool back the temperature, and the cellulose binding domain will refold and regain its three-dimensional structure and its ability to bind a substrate. See, this is what we call a temperature tunable switch. This will allow us to reuse the same batch of enzyme for multiple rounds of saccharification. It could potentially drop the cost of biofuel production low enough that it is actually competitive compared to burning oil. Thank you.